is so that you've looked at this, you see it, you're happy with it, you work it. When you see a real exam, this really cuts down on the panic factor. So you know just what the thing is going to look like. Okay? Let's go ahead and go through these questions. And as we do them, if you have any questions, please let me know. The exam starts with a very simple nomenclature section. We're doing cycloalkanes and alkanes. Once again, because this is only chapters 1 to 4, you do not worry about stereochemistry other than the obvious cis strands or whatever. Our first one, we have a cyclopentane as a parent. We have an ethyl group and we have a methyl. We need to decide who is going to be carbon number 1. This is going to be determined alphabetically by the ethyl group. So this is carbon 1. That will be 2. That will be 3. That will give us our lowest number sequence. The stereochemistry here. In this projection, we've shown the ethyl group up, methyl group down. So we're going to have to indicate that they have trans stereochemistry. Now, if this was chapter 5, we would have to assign R and S to each of these, wouldn't we? But we're not going to do that in this portion. So it's a cyclopentane, it's trans, has an ethyl, has a methyl, trans, 1-ethyl, 3-methyl, cyclopentane. Our next guy.
I have a question.
Okay.
You went counterclockwise?
Yes, because this gives us 1, 3. If we went this way, it would be 1, 4. Our next one is a cyclohexane. We have a chlorine and a bromine on the same carbon. That means that this is by default going to be carbon number 1. We're going to want our lowest number sequence, and so we're going to start here, go counterclockwise again. So our first number is going to be 1, 2, and then 3. No, I'm sorry. We want to go this way, don't we? Because that's 1, 2. So that's the lower number sequence. So we're going clockwise. We have a bromine and a chlorine. They're both on carbon number 1. And we have 2 methyls. We don't have stereochemistry shown, so we don't have to indicate it. 1 bromo, 1 chloro, 3,5-dimethyl cyclohexane. Actually, that's not right, is it? Yeah, it should be 2,5. I'm sorry. So let's change that. 2,5-dimethyl cyclohexane.
I have a question.
Uh-huh.
Do you don't have to put trans or cis?
No, because this is not showing any stereochemistry.
Okay.
It's just a flat projection.
Okay.
This next guy, kind of looks like a logo of some sort, but it is a very simple alkane, isn't it? Our longest chain is going to be 1, 2, 3, 4, 5, regardless how we do this. So we'll just call something carbon number 1. Looks to me like out here on carbon number 3, we have 2 ethyl groups. So this is quite simply going to be a 3,3-diethyl pentane. Our next one, again, we have a couple structures. Let's give them names. When we look at our first one, if we were considering this to be from chapter 5, again, we would have to identify that as a chiral center and do R or S. But we don't right now, so we won't. Looks to me like we're going to have a long chain alkane. chlorine and a methyl group. We want to number the thing starting down here, so our number is 3 instead of 4. And we simply have a chlorine and a methyl at carbon number 3. Our parent is a hexane, 3-chloro, 3-methyl hexane. Does this guy have a chiral center? Well, these are 2 ethyl groups, so that's not chiral. But here, we have this ugly thing, have an ethyl and a propyl. So this is actually a chiral center. So yeah, it is. But we don't have stereochemistry on the thing, so we don't have to worry with that. We need to find our longest chain. I think if we start down here, we could do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. That sounds better. So that's going to be a heptane. And we're simply going to have an ethyl group here and an ethyl up there. Those are positions 3 and 4. And so our name is simply 3,4 diethyl heptane. Any questions on these guys? Yeah.
So in the 3-chloro, 3-methyl hexane,
Well,
we can tell by the wedge bonds which directions the chlorine
Right.
and the methyl group are going in. So did you want us to put cis or trans in?
no, because remember we're restricting ourselves to no stereochemistry other than cis and trans.
So on the exam Tuesday, you'll specifically indicate if we need to say that. Okay.
Yep, yep. Is this RS, just for kicks? Our lowest priority group here is going to be the methyl, right? And it's heading back. So we're going to go that way, that way, that way. That's clockwise, right? That's an R. Good. All right. Let's do this backwards. Here we have a cyclopentane. We're going to have methyl groups in carbons 1 and 3, and the stereochemistry is cis. Lots of ways you could draw this thing. Let's just start off with a skeleton like that. You could use wedge bonds as well. These are our carbons 1 and 3. We want cis methyl groups, so they either both have to be up or down. We start off like that. Then our other methyl group must be up also. Does this molecule contain chiral centers?
Yes.
Yeah, it does. 2 of them. Is it a chiral molecule?
No.
No, it's a meso, isn't it? Nice plane of symmetry up and down the middle. Trans 1-bromo-4-chloro cyclohexane. Now here I specifically say I want a chair, and I want its most stable conformation. So if I was answering this question, the first thing I would do is I would draw a perfect chair. I would show my axial and equatorial bonds in the 1-4 positions. Okay? Now all I have to do is arrange a bromine and a chlorine so that they are trans to each other and so that they are in the most stable conformation. Now remember, when we're dealing with 1-4 trans, the groups could either be both axial or they could be both equatorial. Now, being diaxial would be very, very unstable, and therefore we want to put these things equatorial. To do that, all you have to do is indicate chlorine, the bromine, and of course, put in your hydrogens.
Is that just because they're physically further apart?
Yeah, remember, if they were both axial, you would have huge interactions between these and the axial hydrogens. Be very, very unstable. You would have to ring invert.
Yeah, it's a stretch.
Any questions?
I have another question.
Yeah.
I'm gonna be your best friend today. Could we draw the cyclohexane like that using wedge bonds?
Well, no, because I specifically say I want a chair.
So no wedge bonds in the chair.
No wedge bonds if I say chair.
Can you show, oops, is there any, how would it look if it was cis? Because I was gonna,
Oh, if they were cis?
there'd be one equatorial, one axial.
Yeah. Now remember, they must both be on the same side of the ring plane. The ring plane is like defined this way, and so this chlorine and this hydrogen are cis to each other.
Oh, because they're
This-
both up, right?
Yeah,
Okay.
this is down, this is down, these are cis to each other.
See?
All right, a very simple pentane, a 3-ethyl, 2-methyl pentane. We want to start off with our 5-carbon parent. And of course, you can draw that any way you want. I drew it like that just because I can. In carbon number 2, we want a methyl. Carbon 3, we want an ethyl. I think this would work. Carbon 1, 2, methyl, 3, ethyl. Now remember, we could also look at this and say, okay, 1, 2, 3, 4, 5, that's a pentane, isn't it? And here at carbon number 3, we have an isopropyl group. But that's not as good of a name, is it? Because we want the greatest number of constituents. Isopropyl would only be 1. This way we get 2 of them. All right, once again, trans 1,2-dibromo cyclohexane in a chair. So you start off drawing your perfect chair. You know that if we have, well, let's draw our chair first. And I put the axial and equatorial bonds in. All we have to do is decide where we're going to put our 2 bromines. And remember, they must be trans to each other. We could have both bromines axial. Very obviously, that would be trans. But that would not be the most stable conformation, would it? If we had them both equatorial, they are also trans. Think about it as 1 up, 1 down. And that would be the most stable. That would be our structure.
When is axial the most stable?
When is it the most stable? It almost never is.
For our use
I mean, I suppose you can come up with a particular molecule that would be more,
Yes, go out your way.
yeah, way out of your way.
Would we rather have like a bromine equatorial weather?
If you, well,
Before anything else?
if I said that these were cis, okay, then you would have to put 1 equatorial, 1 axial.
But like if you just had like 1 bromine and then like I don't know, like a methyl group,
Mhm.
would you rather have the bromine equatorial than?
You know, there's a table in the book that has interaction energies. So if you, wanted to look at that, you would decide which one was the lowest energy to put axial. In general, however, bromine is very, very large. It'll be much larger than a methyl. So the bromine would be equatorial. That's just intuitive.
So in that picture, one bromine is up, one is down. That's why they're trans.
Right.
But could I show you like being one on one side of the ring and another on the other side should be trans or no? Or
Well,
the
they
difference?
have to also be 1, 2 relative to each other.
Oh, sure. That's true. But
So you should practice looking at a cyclohexane ring. Make sure that you can draw dye-substituted cyclohexanes for 1, 2, 1, 4 like we did, and also 1, 3.
and to be cis, they have to be both up or both down.
To be cis, they would either be both. To be cis, we'd have this one up, this one up.
Oh, okay.
Or this one down, this one down. All right. And thus up here with a very simple one, we have a pentane. Our pentane has a bromine, an ethyl, and a methyl. Bromine is attached to carbon 1. I would start by drawing a simple pentane. Define one carbon as being number 1, and simply put a bromine on it. All right, that means on carbon number 2, which is going to be here, we need a methyl, and on 3, that's it. We're going to need an ethyl. There's an ethyl, and there's our methyl. Any questions? All right, next we're going to take a simple alkane here, and we're going to represent this as a Newman projection. Now, what I say to the problem here is that in the Newman, I want carbon number 4, this molecule, to be the front carbon, so that's this guy, and carbon 3 as the back carbon. So step 1, we have to look at our simple alkane, and we have to number it. Well, that's not difficult. We're going to let carbon 1 be out here. Carbon 2 has the methyl group, and this is 3 and 4. All right, now remember your instructions. Carbon 4 is going to be the front carbon. And carbon 3, this guy, is our back carbon. So now all you have to do is look at it and say what's attached to carbon number 4. Well, it's a CH2, so it has 2 hydrogens, and it has a methyl group, doesn't it? We want this in its most stable conformation. So we're going to want to arrange our substituents anti to each other, aren't we? So let's go ahead and put our methyl and our hydrogens on carbon 4. Now we look at carbon 3. What's attached to carbon 3? Well, it's also a CH2. So we're going to have 2 hydrogens, and this thing, well, that's just an isopropyl, isn't it? Again, we want the most stable conformation. So we want the isopropyl and the methyl to be anti to each other. So down here, we're going to put our isopropyl, and up here, we have our 2 hydrogens. Everyone see how we did this? You want to go through it again quickly? All right, let's erase everything. Step one, we numbered our chain. Right? Step two, we follow directions. The directions say carbon number 4 is in front, and carbon number 3 is in back. So what we're doing is we're looking down this bond this way. All right, attached to carbon 4, we have a methyl group and 2 hydrogens. Attached to carbon number 3, we have 2 hydrogens, and we have an isopropyl. And that is our Newman. And again, the logic. To get the most stable conformation, we put big groups, the methyl and the isopropyl, anti, or on opposite sides to each other. Now make sure you get this because there's one very similar to this on the exam.
Do you have to put that number on there? You have to put that number there?
No, no. If you wanted to name the thing or whatever, starting from here, I just put that there, so it'd be simple. 1, 2, 3, 4, 5.
What's attached to carbon 3?
Carbon 3, right here. We have 2 hydrogens. So it's carbon 3 is the big ball, 2 hydrogens, and this thing, the isopropyl. All right, we're looking to draw 1, 2, 4 trimethyl cyclohexane. Methyl groups on carbons 1 and 2 will be cis. Methyl groups on 1 and 4 are going to be trans. And again, we want the most stable chain. So step 1, you want to draw a perfect cyclohexane. And you want to put in your axial and equatorial bonds so they're 1, 2, and 4 relative to each other. So you draw your cyclohexane, and at carbons 1, 2, and 4, I put in the axial and equatorial bonds. All right, carbons 1 or methyl groups on 1 and 2 are cis. Methyl groups on 1 and 4 are trans. Now, if our methyl groups here are going to be cis to each other, they both have to be on the same side of the ring plane, right? So they both have to be pointing either up or down. Now we're shooting for most stable. So I would always start by putting a methyl group in the equatorial position. So if we put the methyl group here, equatorial, then the methyl group here in carbon 2 has to be on the same side. So this is pointing down. That means this must be pointing down as well. So step 1. I draw in that center. Yeah.
Would it be better if we just put in the methyl groups? Like, do I have to put in
You have to put in the hydrogens. Yeah. Yeah. Because remember, I've got to grade these.
the
And your drawing won't be as nice as mine. And I need to be able to make sure that you know what's what. All right, so again, I started with the methyl group here, equatorial. Now, I could be wrong. You know, this could be a bad thing. And if it is, I'm going to have to reverse it all. But I'm going to start there anyway. Now, to put the methyl group here, cis, since this is equatorial, that means the methyl group here must be axial. They're both pointing down off our ring plane. All right? So let's look at carbon 4. The methyls in carbons 1 and 4 are trans. That means, since this one is pointing down on carbon 1, this guy on carbon 4 must be pointing up, because they're trans to each other. So we're going to draw this like this. 1 and 4 are trans, and those equatorial. We have equatorial axial and cis for 1 and 2.
So the most stable is always going to be the most equatorial.
Yeah, you know, the rule of thumb is the largest number of equatorials.
Because
Now, there are
Why?
exceptions. There are lots of exceptions to that one. Because if you have a terp butyl, remember, the terp butyl is so large it must be equatorial. So that means that you can have like 2 axial things on something with a terp butyl. So the terp butyl always wins equatorial position. Yeah.
So on carbon number 1, where you have the methyl group going down, could we make that going up for
Yes, we
purposes if
could.
we wanted to?
We could put this going, the methyl going up, but then this methyl would have to go down here.
I'm sorry, that wasn't my question. I'm trying to explain better. So is that, where we have carbon number 1 labeled, is that equatorial space always going down? Will we have
Yeah,
to flip
in
the
the
entire
drawing.
structure? Yeah.
In the
Okay.
drawing, it's already down.
Equatorial is always gonna be down? Is that what you said? The equatorial is also always gonna be down?
Just in the drawing, the way the thing is drawn. Remember, we put axial bonds perpendicular to the ring plane, which means that the equatorials always appear to be down or up. Like that. Just practice drawing your structures. All right, there's another question here. Goes all the way back to Lewis structures. This is general chemistry. Well, let's go ahead and do it anyway. We want to draw the Lewis structure for methanol. When we draw a Lewis structure, we have to remember that the oxygen here is going to have 2 unshared pairs of electrons. And so we're going to have to show those. We basically have a carbon bonded to 3 hydrogens. Going to be a single bond going out to the oxygen, another single bond to the hydrogen, and our 2 unshared pairs. Start with our carbon. It should look like this. Again, the carbon is bonded to the oxygen, and we must show the 2 unshared pairs of electrons. And finally, the oxygen is also bonded to the hydrogen. Any questions?
Show polarity.
I didn't ask a dipole question, but remember the electronegativity of the oxygen is going to be greater than the carbon. So it's going to draw the electrons towards itself. That's why methanol is a reasonable Bronsted acid. Just like water loses the proton, so does methanol. All right, a very, very simple question. Count up the number of sp squared atoms. So this is chapter 2-ish, something like that. Remember, an sp squared center is going to be trigonal, planar, and we're basically talking 3 sigma bonds and a pi system. We have a 6-membered ring here. We have 3 double bonds within the ring. We have a carbonyl, so there's a carbon doubly bonded to an oxygen, and of course the oxygen doubly bonded back. As I count, I can start anywhere. Going around the ring, these are all sp squared atoms. The carbon of the carbonyl and the oxygen are both also sp squared. This pair of electrons on the nitrogen, because it is also trigonal, is exactly in the ring plane here, pointing out this direction. All right, this is a lovely confusing thing. Which of these is 2,2,5-trimethyl hexane? Now what we have here are 3 condensed structures that are just confusing as all get out to me. The way I would do this guy is I would draw the structure. All right, what's this thing really look like? And you can do that because you have the name. This is going to be a hexane. So I start off with a zigzag 6 carbons. We have 2 methyl groups in carbon 2 and 1 in carbon 5. Now all we have to do is find something that's going to match that. Our first one here, I show 2 methyls attached to this carbon, right? So this is going to be 1, 2, 3, 4, 5 carbons in our longest chain. We're looking for a hexane. That's not it. This guy, same thing. We're going to start here with a carbon. 2 carbons attached here. So here's a carbon. That's 1, 2, 3, 4, 5, 6. That's a hexane for a parent. So that's good. Well, remember, that's good. Here we have 1, 2, 3. Remember, this is a side chain. So 1, 2, 3, 4, 5. That doesn't work. 1, 2, 3, 4, 5, 6, 7. That doesn't work. So we're either down to B or the dreaded none of the above. So let's see if B works. We have carbon number 1 here. So I'm going to start on this end. We have a carbon, and then this is carbon number 2. We have 2 more methyls attached. Carbon 1, carbon 2 with 2 methyls. Then we have 2 CH2s here. 1, 2. We have a CH. That's this guy. And to this CH, we have 2 methyls attached. I think that works. Start down here. We have this carbon. Just look at this carbon, carbon number 2. Carbon number 2 has 3 methyls attached, doesn't it? Then we have 2 CH2s, those 2, and a CH with two methyls. I think if you try to draw this without drawing the structure first, it really is much more difficult. So that's just a hint. Any questions?
For the previous one, I just counted up all ones that had triple bonds. So how do you know for sure it's an sp2 atom? Because I just glazed over that before.
Oh, how do you know that they're sp squared? Remember, sp squared is going to be a trigonal sigma network with a pi bond.
Yeah.
So those are going to be what we refer to as double bonds. So you're really looking, another way to say this is how many atoms in this molecule are involved in double bonds. All right, we have 1, 2, 3, 4. Which of these are isomers? Not talking stereoisomers here. Not talking conformational, we're talking constitutional isomers. Simplest way to try to distinguish these would be to, first of all, just generate a quick molecular formula. Remember, if they're isomeric, they must have the same molecular formula. Here we have 6 carbons in a ring. We have a methyl group. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. 5 carbons in a ring. 6, 7. 7 carbons. That's 6 hydrogens. 7, 8, 9, 10, 11, 12. That looks good. Over here, if you look at A and C, they're both methyl cyclohexanes, we will call those. But this one has double bond here, this one is here. Same molecule, double bond, just a different position. So that's going to be the same formula. And finally, this guy, we have 1, 2, 3, 4, 5, 6, 7 carbons, that's good. Hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That one doesn't work. So, looking at our choices, A, B, and C are all isomeric. Any questions on it? All right, what is correct regarding conformational isomerism in cyclohexanes? Okay. In general, the most stable conformational isomer will have the greatest number of equatorial substituents. That sounds like something that we've said over and over again, doesn't it? More equatorial you have, the better the stability. Ring inversion requires complete rotation around a carbon-carbon single bond. No, it doesn't. Remember, I was able to take this model and very, very carefully do a ring inversion. I believe it actually did come apart, but that doesn't count. It doesn't have to. If we did 180, it would have to come apart. Equatorial substituents are disfavored due to eclipsing interactions. Well, that's not really true, is it? Because what we said is A. More equatorial, the better. A and C are correct. Well, C is not. And of course, they're not all correct. Only one that works is A. All right, the next guy here, number 17. I gave you a structure drawn in a boat. Now, we don't like that, do we? And here we have questions about the orientation of our methyl groups. We want to know in the most stable conformation if two of them are axial, two are equatorial, they're all axial, or they're all equatorial. Okay? I think the simplest way to do this is to convert this into a chair, and then take that chair, make sure we have the largest number of equatorials, and go with it. In order to convert this into a chair, something like this, I'm just going to start with these two guys like this on carbons 1 and 2. So here's my skeleton, and I put in axial equatorial on 1 and 2. Now, let's look at our drawing here. Hydrogen is written here above the methyl, isn't it? So over here, hydrogen is going to be up, and the methyl is going to be in the equatorial. This one, hydrogen is also above the methyl, so hydrogen is going to be here, and the methyl here. Now, I haven't moved this one. This one is still sitting just where it was. Hydrogen or methyl above hydrogen. To get this into the full chair now that I've taken care of these two, what I have to do is simply take this carbon and rotate it down to this center. So just that simple thing. When I do that, methyl is still going to be above hydrogen, isn't it? Not going to take any bonds apart. So methyl is going to be above hydrogen. Methyl is above the hydrogen. So what we've done is successfully convert this boat into a chair. Now let's look at the questions. Two of the methyls are axial. Well, no. I have an equatorial methyl, an equatorial, and one axial. Two of the methyls are equatorial. Well, yeah, that's true. That one works. All the methyls are axial. Nope. Nope, we have two equatorials, one axial, and they're not all equatorial either. Therefore, B is the correct answer. Two are equatorial. Now on the exam, you will have, let's go ahead and just erase this. You will have a question or questions similar to this. I want you to be able to take things like boats and convert them into chairs and whatever. So just refresh. How did I do this? I know I have substituents 1 and 2, so I just drew a rough skeleton. Again, our relative geometry. Hydrogen above methyl, hydrogen above methyl. This one we left unchanged. Hydrogen above methyl, hydrogen above methyl. With this guy, methyl is above hydrogen, methyl above hydrogen. So when we move it down, methyl, hydrogen. Any questions? Here we have C2H4O. And I've drawn some structures. Which of these is an improper structure? Well, they all have C2H4O, don't they? Our first one here, we have a carbon-oxygen double bond. Carbon is doubly bonded, one more single, 4 bonds on it, it's happy. It's a carbonyl. It's an aldehyde, remember? And we have 3 hydrogens on this. That's a good structure. It's called acetaldehyde. Here we have carbon-carbon in a double bond. Each carbon is bonded to 4 things. That's good. Oxygen is bonded to one other thing. Remember, it has 2 unshared pairs of electrons as well. This is an acceptable structure as well. We'll see in next semester that we're going to call this an enol. Carbon-carbon double bond is an alkene. This is an alcohol. It's a very special type of compound. We'll see it a lot next semester. This is an enol. Every carbon here has 4 bonds, doesn't it? The oxygen has 2 bonds. That's good. Everybody's happy. It's a cyclic ether called an epoxide. And finally, this guy is just full of problems. We have 3 bonds on this carbon, and oh my goodness, we have 5 bonds on this one. Any questions? All right, formal charges on carbon and oxygen is carbon monoxide. Remember, we want to take our Lewis structure. We want to split the bond down the middle. We are then going to look at the electrons around the carbon, look at the electrons around the oxygen. Carbon now has 1, 2, 3, 4, 5. We look at our periodic table. Carbon is in group 4A. It has 1 extra electron. Should have 4, now it's 5. This is a -1. The oxygen has 1, 2, 3, 4, 5. Oxygen is in group 6A. It should have 6. It's missing 1. Therefore, the formal charge is +1. Any questions? All right, the last group. We were taking things and we were putting them in their most stable conformation. Now here we're going to use just the general rule of thumb that we're looking for the greatest number of equatorial substituents. One exception, of course, is always going to be our tert-butyl. On our first one, we have an axial methyl, an axial, tert-butyl, and we have an equatorial bromine. Our tert-butyl here is going to always want to be equatorial. We've got it axial, that's bad. So, what I would do is I would draw the opposite ring. When you draw your ring, instead of starting with this pointing down, you want to draw it with it pointing up. So you draw the opposite ring. Then you simply go around the ring. This was axial, it will now be equatorial. This was axial, it will be equatorial. The bromine is equatorial, it will be axial. Here's your basic ring structure. Again, I simply, instead of starting down here with this pointing down, I drew the opposite one with it pointing up. I put in my axial and equatorial bonds, 1, 2, and 4 relative to each other. So simply put them in, 1, 2, and 4 relative to each other. Our tert-butyl group is going to be equatorial. Our methyl group here is going to be equatorial. And our bromine is going to be axial. The structure should look like this. We've simply inverted at all of these positions. Tert-butyl axial, tert-butyl equatorial. Methyl axial, methyl equatorial. Bromine equatorial is now axial. Any questions? Just takes a little bit of practice. Practice drawing just the skeleton. Once you can put in the axial equatorials all the way around, the rest is trivial. All right, here we have a boat. And we also have another tert-butyl. And oh my goodness, we know we want to make that equatorial. Well, you know what I would do if I was looking at this as a problem? I would look at the way this is drawn and say, yeah, well, this is pretty much already equatorial, isn't it? We have a methyl group pointing up. This is pointing down. I would draw this something like this. Here, this carbon is this one, just for simplicity. Methyl above tert-butyl. And we know tert-butyl has to be here. Now, just look at your relative geometry here. Hydrogen is above methyl, isn't it? So, when you go to your 1,4 structure, hydrogen is going to be above methyl. Putting our things in, there's the tert-butyl, there's that methyl. Over here, hydrogen above methyl. And it looks like that. All right, our last pair. We have 2 axial bromines, and we have 1 equatorial methyl. We clearly are going to want the 2 bromines to be equatorial, which is going to force the methyl group axial. Our substituents are 1, 3. So, start off by drawing your perfect ring. Put in axial equatorial bonds on carbons 1 and 3. We're going to make these 2 bromines equatorial. Our skeleton should look like this. each of these carbons, we have an axial bromine, they will be equatorial. This one, the equatorial methyl, will now be axial. We make both of these guys equatorial, forcing the methyl axial. Any questions on it? And our last guy, we have a boat. Simplest thing to do is to draw yourself a skeleton. We have substituents 1, 2, and 4. So I put in axial equatorial bonds 1, 2, and 4. Now, if you haven't done this, go ahead and do it. If you've done it, check your logic. If we start here with this carbon, think about your relative spatial geometry. Hydrogen is above methyl. And over here, hydrogen will be above methyl. Just draw that in. Our second one, hydrogen is above bromine. Hydrogen would be above bromine. And our third one, bromine would be above hydrogen. Bromine would be above hydrogen. Filling them in. Hydrogen above methyl, hydrogen above bromine, bromine above hydrogen. Now we look and see if we're lucky, or if we have to ring invert. Here we have 2 equatorials, 1 axial. If we ring inverted, we would have 2 axial, 1 equatorial. So we were lucky. But if you do this on the exam and you're not quite so lucky, what do? Do a ring inversion and draw the other conformational isomer. Everyone got it? Once again, the key to all of this, to all of these types of problems, is being able to draw your basic structure, and then you can just use your relative spatial geometry to fill them in. Now that wasn't so bad. On your actual exam, you will probably have, I haven't written it yet, but you will probably have the same number. What was this? 24 questions, plus 1 extra credit. So total on the exam will be 105 for this portion. It'll be 20 points for the other portion. So exam 1 has a total point possibility without the extra credit of 120. That's going to raise our grading curve a little bit, but it's still going to be the 90, 80, 70 stuff. So no problem, no change. Any questions? Now for the stereochemistry part, please go to Blackboard. Apply the little sample quiz that's there. You can take it as many times as you want. Remember, this one you want to have done by the day of this exam. 3 attempts, and quiz 1 covers all 5 chapters. Any questions? Yeah.
If we can't make it on Tuesday to the exam, if we can't make it on Tuesday to the exam, say like just maybe sick or something like that, would you be able to, would you